All right, welcome to Wednesday's class, Math 332. As you know, we've been looking at testing hypotheses about various parameters. We've looked at mu, sigma, sigma squared, and combinations, two mu's, the means of two populations, the variances of two populations. So now we want to move to another one, theta, the probability of a success in a binomial random variable. A lot of the detail is pretty much the same as what we've been working on, so we can get through this pretty quickly. I have on the board, this is section 5 from the text. We have a binomial population. We're going to think of the parameter n as our sample size. We control how big n is, and our focus is then on theta, the probability of a success. Our null hypothesis is going to be theta has some pre-specified value, theta 0. And of course, we could choose any of the three basic alternatives. And generally, the researcher would have one of those in mind. He would be of the opinion that theta 0 is, that theta is actually smaller than theta 0 or larger. We don't choose the alternative randomly, but it's based on our research thesis. Our test statistic is just going to be the number of successes that we got from our sample, X. And we could use a traditional test, and maybe we'll talk about this in a minute. But right now I'm going to say we're just going to do p-values. We have a binomial population. We know the PDF for that, and we have powerful computers. So not too many years ago, if n was very large, calculating the probability of a given X to find a p-value, it was difficult. And so people found ways to make it simpler. We'll talk about that a little bit later. But for now, we're just going to use p-values. I have the details over here on the right, and then we'll work an example or two. So specifically, we want to test theta equals theta 0 against, I just randomly picked alternate hypothesis theta is less than theta 0. So with that alternate hypothesis, it puts the critical region on the left. You can see the p-value. Here's the expected value. I just drew it in for reference. It's really not a part of what we're doing here. And it's going to be somewhere around the peak. Binomial is not perfectly symmetric, but it's somewhere in the middle. And the p-value, here's our X from our sample. And the p-value is going to be the probability of getting that value or more extreme. The extremity is determined by the alternate hypothesis. So more support for the alternate would be any value less than X. So the p-value is the shaded area. I drew it as a curve. We know the binomial is discrete, and so really it's a bunch of bars underneath there. You can see I wrote curved in quotes there just to let you know it's an approximation. All right, so we can find the probability that a binomial random variable with parameter theta 0 and n, our sample size, takes on a value less than or equal to X. There it is. We just calculate that quantity. And we compare it to our favorite value of alpha. Or, we could just state the p-value and let the reader make their own decision. They could use their own value of alpha. Now, like I said, not too many years ago, if n was for large, this was a tedious calculation. Most of us would probably say it was an impossible one because we weren't patient enough to do the work. But these days, it's nice and easy to do. And so I'm going to say this is a little bit different than the textbook, but the textbook doesn't assume that we're using modern technology. And I'm going to say our go-to method for testing this hypothesis, theta equals theta 0, is just going to be to find the p-value. I'll do an example in just a minute. I did the calculation with my TI-89, and it took it about 7 seconds. So not too long. For somebody from my generation, not long at all. For someone from your generation, maybe that 7 seconds is a terribly long time. But we get a more accurate answer, and it's worth doing. Just point out that if the alternate hypothesis were that theta is unequal to theta 0, then we would calculate the p-value and then we would double it, because our critical region would have two pieces. That is, I get evidence that theta is not theta 0 if I get a value to the extreme left or to the extreme right. Either of those cases would support that theta is not theta 0. So I would just do this calculation and then double it. And if that were the alternate, I would write a 2 in front of my sigma, so I'd be writing true things on the board. Anyway, I'm going to pause you for a second and convert the board to the example I want to work through. All right, I've chosen problem number 63 from the book, chapter 13. If you read 63, it probably supplies a context, like what in the world are we talking about? And I really don't care here. Just want to grind through the details. So they tell us in problem 63, they sampled 225 members of the population, and they got 65 successes. Now, just for a point of reference, notice the alternate hypothesis. It's the same one we talked about earlier. It's theta less than 0.35. If the null hypothesis is true, the expected number of successes in theta, plug this in, and we get 78. So we got 65. That's some evidence that theta 0, 0.35, that it is too high. But the question is it significantly below? Is 65 enough below 78.75 that we can say that probably the null hypothesis is not true? Well, that's where we need probability theory, which we have. Here's my p-value. I just sum, like extreme or more extreme than 65. Well, with our alternate hypothesis, our critical region is at the left. And so I just sum, and that's the calculation right there. I said it took my 89 about 7 seconds to do. And I came up with a value 0.0306. That's the p-value. That's a small value. And so we're going to reject the null hypothesis with authority, not with factorial. If the alternate hypothesis would have been two-tailed, that is, theta is not 0.35, without a bias, is it less than or greater than, then our p-value would be doubled, and then we'd be sort of getting into shaky ground. A p-value bigger than everyone's favorite alpha, 5%. Still pretty small, but that's not what we have. We have one-tailed test, and so we can pretty confidently reject H0. Now, let me show you the way that this would have been done when I was a statistics student, and up to, not that long ago, maybe 15, 20 years. And this is the way the book shows us. And that is, as we know, for certain conditions, I think our conditions were dependent upon the expected number of successes and failures. And let's say that we require both of those to be at least 10. We've talked about a couple different values. We'll assume 10 for now. Then we can approximate a binomial population with a normal. So let's call this the traditional method. And I'll just say if n is large enough, and I'll be vague there, but I just told you what that means, really. Then x minus n theta, the mean, divided by the standard deviation, n theta times 1 minus theta. We're going to treat as a z. Maybe we could say it's approximately standard normal. We'll let z tell us standard normal. Some people divide through by n, and if you do that, we get x over n. Remember, that's our favoritist estimator for theta. We call it theta hat. and minus theta divided by, if we divide by n on the bottom, it gets squared when it goes under the square root. So we end up with, these should all be theta zeros because we're assuming when we do the calculations, the null hypothesis is true. So we have theta 0 times 1 minus theta 0, and we'll divide by n. You can think of it either way, it doesn't really matter. I think for the calculations I have, I'm thinking of it the first way. Okay, so let's solve this problem by the traditional method. We'll use the standard normal. So what I need to do is find the z-score corresponding to our sample value. And so we're going to plug in 65. Find the z-score for x equals 65. This is a little z. 65 minus, I believe I have the n theta right over here, 78.75. We'll reuse it. Then we divide by the square root of 225 times 0.35 times 0.65. I've done that calculation. 1.92, of course, negative. So how big is that z-score? You ought to know right now, like, that's a pretty big z-score. It's hard for a value to be 2 standard deviations away from the mean, and we're super close to that here, negative 1.92. So I go to the table. So now we're looking at a standard normal. And we want to know how much area is below negative 1.92. Just like before, the critical region at the left with our alternate hypothesis. And from the table, I get 0.0274. This would be the p-value. Did I say 2724? 274, that's all, 0.0274, that's what I have. You can see that's quite a bit less, percentage-wise, than our p-value over here. You know, maybe that's just the price you pay from approximating. We did not approximate here. We used the population PDF. Over there we did. So we like this value better. We would have the same conclusion here, 0.02. That's even smaller. So we would reject it. When I was a student, I wouldn't know about this, and I would just say, oh, look at that. Except, remember, when we approximate a binomial with a normal, we have that thing called the continuity correction, right? The normal takes all the area under the curve, where the binomial, it concentrates the probability at integer values. And so we lose the probability that lies between integers. And remember, can you see this? I got a little room. Using continuity correction, well, we slip halfway away from our actual value. And we want to, 65 is our actual x value, so we want to include it. So we're in our critical regions to the left, so we're going to slip up to 65.5. So here we're going to let x be 65.5. So we're going to add just a tiny little sliver. The area that lies between, this is the standard normal, but on the original normal, we're approximating. 65 would be here, 66 over here. We're just going to take half of that. Not quite half because the curve is increasing, but we're just going to choose the halfway point. And slide that area in. So if I replace 65 with 65.5, I'm not going to go through the calculations, but I will tell you the result. 0.0322. And you can see that's closer to the actual value than without the continuity. And you know, the continuity correction is just better. And it's not harder. We just use a different value. We're not doing any of these calculations by hand. So the calculator doesn't care if we're plugging in 65 or 65.5. It's super good at it either way. Okay, so in the end, our go-to technique for these hypotheses, theta equals theta 0, versus either of the three alternatives, it's going to be the p-value. And we have a complicated, without a calculator expression, we're not going to panic. Our calculators can do it. We're willing to wait 7 seconds. It took me longer than 7 seconds to type it in. Wolfram Alpha would certainly calculate it faster, but it might take you a little longer. But that's what we're going to do. We're going to understand that there is a traditional approach. I mean, if you look in the book, they're not going to say do this. They're going to say do this. And they may even make it even more traditional, that is, find the critical value Z alpha. Notice, because we're talking p-values here, we didn't talk about Z alpha over to those critical regions. We're just using p-values here. And we'll make our assessment based on those. But once I convert to the Z, pretty much everything is like what we did for means, for the first case, or for mu, when we had large samples, and before we had to use the T. So all three ways give us pretty good data that we really need to reject H0. So once again, this is the very best way to do it. With continuity correction, it's the second best. And without it is third best. Still decent, but we can do better. All right, I'm going to pause this video. Actually, I'm going to stop this video here, and then I may or may not, I probably won't do another one where we work through problems, because it's pretty straightforward. Instead, I'll give you an assignment. You can look on Foxtel for it. I made an assignment on Monday. I think I put 3 problems. So look today, there ought to be 2 or 3 more. All right, and next we'll talk about, if you think about the progression here, first in chapter 13, we learned how to test the mean of a population against a value. And then we went to the mean of one population against the mean of another. We talked through all the cases there. And then we focused on the variance of one population. And then we went to the variance of 2 populations. That's a really handy test for us, because we've assumed in the past that if our populations have the same variance, then we have something to do. And so we need to know, do they have the same variance? Almost certainly S1 and S2 will not be the same from a sample, but is the difference statistically significant? When we apply probability theory to it, we can decide. And now we've talked about theta of one population. Well, guess what's next? Theta of more than one population. There are a couple of ways we could do it. We're going to do it a little bit different way than we've done means and variances. And it will lead us to some other kinds of tests we can do later. So that's it for now. Do your homework. Talk to you for Friday's class.